So this is the picture of what we got for projectile motion for our object that is moving across this cliff at 10 meters per second, and all of a sudden the cliff goes away, or the cliff exists here, and it starts falling. And so remember, I had two motions happening simultaneously yet independently. This horizontal motion at constant velocity, this vertical motion of, in this case, increasing speed because it's accelerating downwards. We said that this forms a parabola. Now we'll prove that together during class. But what I want to do here is a few things. Before we get to do a problem, just so I can illustrate the methodology, I want to show you what's going on with the velocity vectors here. If I look initially, when it leaves the cliff, the initial velocity in the y direction is equal to 0, because it hasn't started falling yet. But we know it's going to start accelerating downwards once it leaves the cliff, and therefore it's going to speed up vertically. But horizontally, it maintains the same velocity horizontally at every point. So I'm going to draw in a horizontal velocity vector at every single point. So there we go. And notice here, I made these horizontal velocity vectors the same length because the magnitude of the horizontal velocity is not changing through this problem because there's no force acting horizontally on this object during the motion. Now vertically, initially the vertical velocity is 0. But then after a little bit of time, we know it's going to speed up. If I wanted to calculate that, I could calculate VFY is equal to VIY plus AYT. And so, for example, if VIY is 0, after 1 second, it's accelerating at 9.8 meters per second downwards, and we'll make down and to the right positive for this problem. This object, after 1 second, would be going 9.8 meters per second. So I'm just going to draw in a velocity vector there. It was 0 there, and it's something there. After 2 seconds, now 9.8 times 2, 19.6, it's twice as big, right? Okay. By the way, I'm not scaling the x to the y, but I'm scaling the y's relative to each other. After 3 seconds, once again, that velocity vector has gotten bigger. After 4 seconds, again, that velocity vector has gotten bigger. So the y velocity instantaneous, excuse me, at every instant is getting larger and larger and larger because I'm accelerating downwards and I'm moving downwards, meaning I'm speeding up. But horizontally, I'm staying the same velocity. But if I were to actually talk about the velocity vector itself, that wouldn't be the x component or the y component, but the net result of those. So if I were to draw that vector addition, that would look like that, and that would be the instantaneous velocity vector. Notice here, the instantaneous velocity vector here is going to be longer because the y component is longer, the x component is the same. And what also changes, hopefully you'll notice, is that that vector changes direction, right? It is here, initially the velocity vector is entirely just the x vector. Now it's tilted downwards. Now it's even tilted downwards more. Here it would be tilted downwards, whoops, that's not great, even more. And here, even more, right? At each point though, what we want to notice, this is not the best picture here, but at every point, the velocity vector is tangent to the path. Now I want to give a nicer name to the path. The path we're going to call the trajectory. Okay? So the trajectory of an object in projectile motion is the path, which in this case, we know that that path is a parabola, or at least we have observed it to be so. We'll prove that, as I said, later. But therefore, that overall speed of the object is changing because the vertical component of the velocity is changing. If I wanted to know what the velocity or the speed of the vector is at any point, that would just be the sum of the squares of the instantaneous x velocity, which is always the same as the initial x velocity because it's not changing, plus the instantaneous y velocity at that point, which we could calculate using that expression. Okay, so since that's staying the same and that's getting bigger, obviously the speed of the, not obviously, but the speed of the object is increasing as it goes along. Notice when I talk about speed, I'm not talking about x or y. Speed is a scalar. Therefore, I should just talk about it in and of itself. And this is a classic understanding of what's going on here, right? That the x velocity is maintaining the same velocity, the y velocity is, in this case, increasing. And I keep saying in this case because this is a very particular type of problem. Notice initially our object is projected horizontally, that the initial velocity of the object is entirely in the x direction. We'll do problems later where the initial velocity is not in the x direction, that there's also a y component. But we'll see those problems later. So let's look at a typical problem. A typical problem might read something like this, right? An object is traveling at, I don't know, 15 meters per second when it goes off a cliff that is 65 meters high. And then there's a couple of questions. I'm going to ask, how long is it in the air? B, I'm going to ask, what is the range? And I will define that in a couple of seconds. And C, what speed does it hit the ground with? All right. So first, vocabulary, range. So if you've heard that before, maybe you've heard of a driving range or a shooting range, right? So a driving range is a golf range where you go and you try and hit the ball as far as possible just to practice your club swings. So the range is only about how far it travels horizontally. So the range, by definition, for this class is going to always be the total x displacement. So there we go. So I'm going to do this problem, and we're going to use the same methodology we used to do our kinematics problems from before. So this first step was to draw a picture. And so I've got a picture. So here we go. Here's my object. It's being projected out this way. There's my initial velocity. I'm going to label the height of the hill to be 65 meters there. And there we go. There's my picture. Step 2, axes and declarations, as always. And so I'm going to say here, down is positive in the y. So that's my positive y. And then positive x is going to be to the right. Here, it makes sense to make the y direction positive downwards because this ball is only ever moving downwards. Make our lives easier. Step 3 is, before we write down our nodes, we want to think about partition. Here, there's only one part of the motion, just that downwards part of the motion. But, and this is the key thing for projectile motion problems, the partition that we're always doing in projectile motion is we're going to do the x motion separately from the y motion. And so here we go. We're going to go delta x, vix, vfx, ax, delta y, viy, vfy, and ay. And if you notice that I've got this space down here, what that's for, folks, is the time. Now, why would I put the time down here? Well, very simply, time is the thing that connects the x and the y motion. Remember, we said projectile motion was two independent motions, x and y, happening simultaneously. So time is the glue that puts it all together. So now that we've done our partition here by dimension, we're going to write our nodes. Well, here, that's my answer to part B, so I'm going to leave that alone. Vix. We know initially this thing is moving 15 meters per second, so just the context of the problem, even though it doesn't say that that's the x velocity, I know because it's projected horizontally from this picture, right, that doesn't make sense to do anything else, that's that. Now, what else do I know? Well, I know it's projectile motion. There's no horizontal forces. That means that the x acceleration is equal to 0. Now, that piece of information, ax equals 0, is not written in the problem, but it's encoded in the context of this type of problem. So I box that because that's a piece of hidden information that we're going to have to be able to look at this problem and see. Now, because ax is 0, I know that the fx then has to also be positive 15 meters per second. I don't have to do any work to prove that. It's sufficient to say 0 meters per second, and therefore that's the same. Now in the delta y, well, I know that it's moving downwards, it displaces downwards, so that's a positive displacement because I said down is positive, so plus 65 meters. And here, if it's a horizontal projectile, the hidden piece of information here is that VIY is equal to 0. So I'm going to box that too, because that's not told to you in the problem, but that's implied heavily by the context. So once again, I don't know that. AY, well, here I know, once again, implied by the context, I know that that thing is in free fall, because gravity is the only force that's acting on that thing vertically during its motion, so there we go. So there's two numbers in here, yet I have, look at all the given information I have. So that's true about most projectile motion problems, is that there's all this quote unquote hidden information. Right, step 1, picture. Step 2, axis and declaration. Step 3, partition. Step 4 is going to be knowns. Unknowns is step 5. I know delta x, I know t total, and then here, what speed does it hit with? We'll deal with that in a minute, because I actually don't have that on my chart yet, because what I need here is Vf, the magnitude of it, right? Speed, neither x nor y, but both simultaneously, so it goes below the bar since it doesn't belong to either x or y. So here I go. So what I'm going to do is I'm going to do this problem, and I'm going to think about my motion equations, but separately in x and y, and I'm actually going to divide my paper in half. So one equation I could go with is delta x is equal to vixt plus 1/2 at squared. And I look at that and I go, okay, well actually ax, I know that that goes away. Now, the most common error that people make is they plug in x information into y equations and y information to x equations. We just can't do that. It's disastrous if we do. So notice here, I need to find the time in order to do this because I have that. So that's not enough. Now, I'm not going to erase that. Well, A, I wrote in pen, but B also, because I know I'm going to need that eventually. So let's go over to the other side and think, well, I've got delta y, VIY, AY, T. Ah, that's what I'm looking for. So it looks like I should use the equation of motion in the y dimension. There we go. And in this case, folks, this term goes to 0 because it's a horizontal projectile. And if you notice, I can now solve 65 meters, 1/2, 9.8 meters per second, t total. Okay, let me just grab my calculator. Let's see what I've got there. Okay, boom, 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 boom. All right, square root of quantity, and I get t is equal to plus or minus, because remember, square root, 3.64 seconds, get rid of the minus sign, and we're good to go. I have my first objective solved. I know the total time that that thing is in the air, so I sketch that path. There it goes. It takes 3.64 seconds to fall. Right, notice if I just drop that object, it would also take 3.64 seconds to fall, right? So here's the thing, if that's the time it has to fall, that's the time it has to move over to the side. And so I take the time that I found in the y, and that's my link over here to x. So I have 15 meters per second times 3.64 seconds equals. And so 15 times 3.64, and that gives me 54.6 meters. And that is my range. So where is that? Very simply, that's from the bottom of the cliff outwards. That's the distance or the displacement that it goes horizontally. So check, check. Now, what speed does it hit with? Here's the thing. The velocity vector, when it gets to this point, is angled like we saw on that other one, meaning it has both an x and a y component. Well, I know the x component's 15, but I don't know the y component. So to solve this problem, I would need to find the y component. So I could just do VFY is equal to VIY plus AYT. I could have also have done VFY squared is equal to VIY squared plus 2AY delta y. I think this is just easier given what I know. I know that this in this problem goes to 0, and so I've got 9.8 meters per second times 3.64 seconds. And that gives me, that gives me 35, with rounding, 0.7 meters per second. Right, so that's just the y component. That's not the answer to the problem. The answer to the problem is, what is this VF? And notice here, that's VF, that's VXF, VYF, or however you want to order your subscript. And we said before that that just makes a nice little triangle, so I know I can solve that using the Pythagorean theorem. Super simple there. This is just the magnitudes of these velocities squared. And so that gets me then 15 meters per second squared, and then 35.7 meters per second squared, and then I can then plug that into my calculator, square root of answer, and I get 38.7 meters per second, and that is the speed that it's going. Now, let's say I was in an ordinary mood, and I said rather than the speed, I said what was the velocity that it hit with. What else would I need? Well, I would also need direction. Very specifically, I need to find that angle. And that's pretty simple then, folks, because if I've got the x and the y components, it's just the arctangent of Vy over Vx at that point, and then I could find what that angle is and then report it as 38.7 meters per second at some angle below the horizontal, and I'm good to go. So just one extra step on that problem if we're asked about the final velocity. So what are we going to do from here? We'll practice these types of problems before we just slightly make them more and more complicated. We have some additional theoretical ideas to talk about in terms of looking at acceleration with this, but I want to do that when I'm face-to-face with you, or at least Zoom to Zoom with you, so that we can talk about that with questions. But that is modeling problems with projectile motion. Pretty straightforward based on the whole concept of how we approach kinematics and this idea of separation of variables of x and y, the same way we approached forces.